guys, this is Mark Yeager with Structural Integrity Associates. I'm here with my colleague, Mr. Andrew Crompton, at a nuclear plant which shall not be named. We are doing some impact testing of small bore branch lines coming off of a pump seal. So here you can see the line in question that we're looking at. The initial connection is here inside of the pumping chamber. It's got a localized flange, and it comes out into a mess of spaghetti. This line has obviously seen a significant amount of thermal working, and it looks like at some point in time somebody got mad at it and twisted it. So it's quite bent. It's got some unique features. So there's support back here for you piping analysts in the world. That support is actually anchored to the wall about 4 feet away. What that means is that when the pipe gets impacted and moves, the support itself actually moves with it. You can see here locally that the pipe has a significant vibration quantity. I'm going to try to anchor my camera a little bit better to just show you how much it moves naturally. There's a very slight breeze in here due to the containment chillers, and the piping itself is moving up and down consistently with that breeze. It's very easy to excite it with just a little flick of your hand and get it moving. You can probably do a quick rudimentary estimate of the natural frequency here without us doing any kind of fancy testing to tell you that. That being said, we are going to do a fancy test for demonstration purposes. So to quick walk you through this, the reason for doing the testing is that we're concerned about alternating stresses on this component right here. That socket weld and these socket welds. These are pretty good welds. They're pretty high quality. They're definitely not 2 to 1, so they're not following the current ASME recommendations. So you're seeing a little bit of a high stress concentrator, in particular in here at the pump, which is the attachment point. So what we're trying to do is make sure that we don't have any natural frequencies that align with the pump running modes, because that's when you get into a resonance condition and you have failures that lead to RCS system inventory losses. So we've already been testing this line a little bit. We didn't want to show you a completely raw demo. We had a sensor mounted right here initially. We just had these sensors mounted on hose clamps. We use Tri-Axial Accelerometers. And the reason for that is we can get all 3 directions with one impact. So we can get an idea of excitation in different directions and how it impacts the system as a whole. As you can see, these sensors are real small. They're less than an ounce, just a little over an ounce with the hose clamp installed. Integral cable. And what we do is run that over here to an analyzer. So we've got a nice fancy laptop sitting here inside the plant with us. We've also got our little analyzer box over here. So we actually have 2 sensors hooked up. I showed you the first one. The second one, if you can see it, is actually all the way back here by this second flange. The reason we did that was just to get a better idea of total system response across this spaghetti mess of piping. So that being said, Andy and I are going to demonstrate a nice little impact test for you here. I am using a calibrated impact hammer. So this little guy right here is synchronized with my analyzer. What that means is that we can take a frequency response function through the analyzer and we can get an idea of the impact that this hammer puts on the piping system. We can measure that consistently in phase relative through all channels so that we get accurate results on our frequency magnitude plots. So we've tested this line a couple different directions. What I want to show you is the vertical response. So Andy and I are going to work together as a team. We're going to impact this line. So I'm going to hit it right here, and we're going to watch what happens in terms of the analyzer itself. So that's a typical impact. You can see there's barely any force to the point where I may be shaking the camera more than I'm actually shaking the pipe. You can get good and bad impacts. You can get ones that glance off to the side like this. And when Andy sees that, he's going to tell me that was terrible, and we're going to repeat that particular test. So what we're looking for is a nice sharp grab on the pipe. Nothing fancy. We just don't want to glance and blow off the side. And we also don't want to double tap. When we try to swing this hammer down, especially if you have a really sharp tip, you can end up double tapping. So you can see here, I know it's a little blurry and I apologize, but we've actually deformed this tip a little bit through testing. That's a good thing though, we're getting a nice clean response to the system. So what we're going to do is impact this about 4 times. And the reason we're going to do that is we take an average when we do our frequency response functions. That average lets us do a couple of different things. Number 1, it weeds out noise in the data. And number 2, take a whole lot of time to hook up. We got everything on the ground, and all the testing completed on this particular line in about 15 minutes. So within 15 minutes, we have a good idea of what frequencies we're seeing on this particular line, and whether those are going to be a problem during operational testing and continued operation. Thanks for tuning in to this episode of Show to be Named in the Future, and we'll see you next time. Thanks, Andy.
Nice.